Good morning, dear students. Today we are going to discuss about electromagnetic induction. As the name indicating, it is a phenomena in which both electricity as well as magnetism are involved. It is put forward by the famous scientist called Michael Faraday. I hope you are familiar with Michael Faraday, right? He is the greatest scientist who have given a large number of contribution to the world of science. Okay, not only in physics but also in chemistry as well. Okay, so according to Michael Faraday, in electromagnetic induction or the phenomenon of electromagnetic induction says that whenever there is a change in magnetic flux linked with a conductor, there will be an induced EMF in it. Okay, or an EMF will be induced in that conductor. Quite confusing, right? Okay, we will get rid of that. You just consider the setup. We are having a solenoid which is connected to a galvanometer. As you see, there is no source of electricity in this circuit. And we will be having a bar magnet also. Suppose if I am bringing this bar magnet closer to the coil in this direction, you can see that there will be a current which is flowing in this coil, so that it will be giving a deflection in the galvanometer. Okay, and the direction of the current will be in this direction. So we will be getting a deflection in the galvanometer towards the right hand side. Understood? And in this case, a south pole is coming closer to the coil. And we will be getting a current which is going in the opposite direction. That means the current will be going in this direction, which will be giving a left-handed side deflection in the galvanometer. Okay, and not only when the magnet is coming closer to the coil, but also if it is moving away from the coil as well, will be giving a current in the circuit. Understood? And the direction of the current will be just opposite to these cases. Okay, and which is giving this direction that we will be discussing later. Okay, first of all, we will discuss about our electromagnetic induction law, which is put forward by Michael Faraday. So Michael Faraday says that whenever there is a change in magnetic flux linked with a conductor, magnetic flux, as we know, which is represented by phi b, and that change is denoted by d phi, and thus dt indicating that the change with respect to time. Okay, that we will discuss why. Thus, a rate of change of magnetic flux will be giving us the induced EMF. Okay, the induced EMF is equal to d phi b by dt. Okay, but there is a correction in this equation. Okay, that correction is given by the scientist called Emil Lenz in Lenz's law. Okay, what is Lenz's law? Nothing but simply adding a negative sign in this equation. Okay, this negative sign will be indicating the direction of the current which is flowing in the circuit. Okay, from our Michael Faraday's equation, we are not getting in which direction the current will be going. Whether it will be going in the clockwise direction or anti-clockwise direction, that we don't know. Okay, that is given by our Lenz's law. Okay, and Lenz's law states that the induced EMF which is produced in the coil will be always opposing its very cause. Means whatever be the cause which is producing the induced EMF, it will be opposing that. Means in this case, the magnet is coming closer to the coil, right? So if the magnet is coming closer is the reason for the induced EMF, then the induced EMF will be opposing this motion. Means it will try to push this magnet away. How that will be happening? We have studied about our Christian Easter's experiment. That is, whenever there is a current flowing through a conductor, a magnetic field will be produced around it. That means here in the solenoid, there will be a magnetic field produced in such a way that it will be opposing this motion. Means here we will be getting a north pole produced as this magnet is coming closer to the solenoid or the coil. Okay, so what happens? This magnet will be pushed away. Okay, so if north pole is produced, then the current direction of current will be like this. Okay, and in this case, if south pole is coming closer to the solenoid, then south pole will be produced in this part of the solenoid. And correspondingly, here north pole will be produced as well as here south pole will be produced. Okay, how we will know whether a north pole is produced and this is the direction? For that, a simple trick is there. I will show you. Suppose if north pole is producing, according to our Lenz's law, if north pole is producing on this side of the solenoid, you just write N. Okay, and just give a slight arrow like this. This will be indicating the current in the coil will be going in the anti-clockwise direction. In the same manner, if a south pole is produced at the coil, at this side of the coil, then you simply write an S and put arrow marks. This is showing that the current will be going in the clockwise direction. Understood? Wherever in the coil south pole is produced, the current will be going in the clockwise direction. Wherever north pole is produced in the coil, current will be going in the anti-clockwise direction. So, since the motion of magnet is towards that side, I will be checking the pole of the solenoid from this side. Okay, so as I see, the current should go in the anti-clockwise direction. So this is the only possibility. Okay, so that we will be getting a right-handed deflection in the galvanometer. Similarly, here in this case, we will be getting a left-handed deflection in the galvanometer. Okay, now we have discussed about what is electromagnetic induction. Suppose if we want to increase the amount of current or EMF produced in this circuit or in the coil, how we will increase that? Okay, for that purpose, we can either increase these number of turns of coils. Okay, we have studied that in a solenoid, the amount of magnetic field produced can be increased by increasing the number of turns of coils. That is one way of increasing the EMF. Next thing is using a stronger magnet. Okay, here in this equation we can see it is d phi by dt. Okay, d phi by dt. So if you are increasing phi, that means if you are increasing magnetic flux. What is magnetic flux? We have studied, that is the amount of magnetic field lines which is coming or which is passing through a surface. Okay, so if you are using a stronger magnet, more number of magnetic field lines will be there. Okay, so that will be linked with this conductors. Okay, and that will be changing while it is moving. Understood? That is another way. So using a stronger magnet or using large number of coils in the solenoid. And the third point is that by moving this magnet or by moving the coil, okay, the relative motion should be fast. Okay, if you are increasing the velocity of the relative motion, then again you can increase the amount of induced EMF produced, because here we are having a dt term, right? Okay, so if the rate of change of magnetic flux is faster, okay, then again we will be getting a higher value of induced EMF or higher value of induced current. Okay, I hope you understood. That's all. Thank you.